All right, so welcome to page 12 of the proton NMR packet. Sorry that I'm just now getting this up. I will leave this video up until Thursday night around 11:59, and then after which I will take it down. So let's go ahead and get started with respect to trying to resolve what the structure of this compound is. Now, recognize that I've given you the molecular formula of this compound, and remember, every single time you're given a molecular formula, what you should do initially is to determine degrees of unsaturation. So take a moment and try to determine degrees of unsaturation, and then I will write the degrees of unsaturation down for you. So hopefully everybody has determined that there are 5 degrees of unsaturation associated with this compound. Now recognize that this could be any combination of rings and double bonds or triple bonds. But as we start to get into determining the structure of this compound, we will recognize exactly where these degrees of unsaturation are based on the peaks that are at certain places on the ppm scale. So let's go ahead and dive into our NMR and see if we can begin to resolve the NMR spectrum. Now, this first peak that shows up around 1.8 or so, this corresponds to a singlet that integrates to 6. Now recall, a singlet corresponds to a group of hydrogens that have no neighboring hydrogens. So this means that there are no neighbors of a different type. Now also note that this integration value is 6, and we know that 6 will correspond to the fact that there has to be some symmetry associated with these hydrogens that correspond to this peak. And we know that there must be symmetry associated with the hydrogens that correspond to this peak because of the fact that we know we can never have 6 hydrogens attached to 1 carbon. So now what we have to do is to try to figure out structurally what could these 6 hydrogens represent. Now remember, whenever you are trying to figure out structurally what a set of hydrogens could represent, you always have to try to deal with the simplest possibility first. We know that these hydrogens must be attached to some carbon that's sp3 hybridized because they don't fall in the vinylic region. We also know that these hydrogens can't be the hydrogens of an alcohol because we only have 1 oxygen, and we would have to have essentially 6 oxygens in order for this to be an alcohol. So we know that essentially the simplest possibility would be that we have 2 CH3s that are associated with this peak. Again, this is the simplest possibility, and we want to roll with the simplest possibility first because it's the easiest thing to possibly rule out. So structurally, we know that this peak that integrates to 6 is most likely going to be 2 CH3s, which are equivalent. And again, these 2 CH3s will have no neighboring hydrogens of a different type. Next, what we want to do is we want to move to the next peak down on our spectrum. And we find that this next peak will correspond to some peak that integrates to 5. So there are 5 hydrogens. Now, note where this peak falls. This peak falls in the aromatic region. So this is an aromatic region peak. And remember, when we discussed this initially, anytime that you see peaks in the aromatic region, this most likely means that there is a benzene ring present. Again, if you go into higher up levels of organic chemistry, you will have to deal with spectroscopy where you are not really allowed to make this determination. But based on the level of organic chemistry that you guys are studying, it's safe to make this assessment at this point. Now, what you need to ask yourself is, how many times is this ring substituted? And what I mean is, any one of the 6 hydrogens that are attached to this benzene ring can essentially be removed and replaced with some substituent. And so if this ring is unsubstituted, there will be 6 hydrogens attached to the ring. Now count up the number of aromatic protons that we have. We have 5 aromatic protons. And so if we have 5 aromatic protons, however, we know that if this ring was unsubstituted, we would have 6. We know that there must be 1 substitution. So if we don't make a substitution on this ring, we will have 6 aromatic protons, and we know that we only have 5. So we have to get rid of one of the aromatic protons, and we'll replace it with X. We don't know what X is yet. It could be some carbon that has methyl groups attached. We're not sure at this point. But we're going to place X so that we can get rid of one of these hydrogens, and it will knock our hydrogen count down to 5. Now, once we've done this, we've basically pulled all of the information that we can out of this peak. Remember how I told you guys during the workshop that oftentimes, even though there are a bunch of different types of hydrogen potentially in the aromatic region will often have overlap, right? So the hydrogens, even though they may be different, their peaks might overlap with one another, so you will end up with a big blob in the aromatic region, which is what we see in this case. But we know that this aromatic ring is at least monosubstituted because we have 5 aromatic protons. Now let's move forward to this peak here. Now note this peak is a singlet that shows up at less than 10, so it's about 9.8. Now, based on the region that this peak falls in, everybody should recognize that this corresponds to an aldehyde proton. So now we have structural features that amount to 2 methyl groups, 1 benzene, and then 1 aldehyde. And we know that the aldehyde only has an ability to make one other bond. That's why my squiggly line is attached to this side of the aldehyde. Now, let's count up the number of carbons that we have accounted for. We've accounted for 2 here, plus 6, that's 8, plus 9, okay? That's 9 carbons that we've accounted for. And we've accounted essentially for all the hydrogens in our structure. We've also accounted for the oxygen in our structure. But note that we still have 1 carbon that we have not accounted for. And the question here is, where is the carbon that we have not accounted for? What can we conclude about the carbon that we have not accounted for in this instance? And we did a problem similar where I asked this question during workshop. And the answer to that question is that for this particular carbon, we can conclude that there are no hydrogens on it. And if we add in a carbon that has no hydrogens, essentially we have all of the fragments that most likely correspond to this compound, and it's now time for us to put the structure together. So what I would suggest that you guys do is push pause on this video and see if you can come up with a reasonable structure. Now, remember, when we discussed this in workshop, I told you, once you think you have come up with a reasonable structure, check the splitting of your structure without looking at the graph to make sure that the structure that you've come up with will match the splitting of the graph. That's the best way to double check yourself. If your splitting does not match, you know right away that you're wrong and you need to go back to the drawing board. So again, push pause on this video and try to piece this structure together. Oftentimes, when students are learning NMR for the first time, you guys will try to look at the answer too quickly. And you really have to struggle with these problems in order to get them right. And again, the only way to really get this stuff down is to continue to practice. All right, so hopefully you guys have taken some time to see if you can piece this structure together. And so I'm going to go ahead and draw the structure of the unknown out. This corresponds to the structure of your unknown. Again, if you're having difficulties with this, you're going to have to just struggle through it. But as you guys start to practice, you will get through these NMR problems a lot more quickly, and you will feel more comfortable with the process of learning NMR as you guys move through these. So let's move to the next problem. So in this problem, we're dealing with a molecular formula. And again, what we should do first is we should always calculate degrees of unsaturation. So note what's happening here. Our degrees of unsaturation here are 5. So we have 5 degrees of unsaturation. And now that we have 5 degrees of unsaturation, we should move into the NMR and try to figure out what's going on with the fragments that we have. So let's take a look at this first peak. We have a triplet that integrates to 3. We know that a triplet means that there are 2 neighbors of a different type. And since this integrates to 3, again, looking at the most reasonable structural feature that could amount to this triplet, the most simple structural feature that could amount to this triplet, most likely this is a CH3. Now let's take a look at this peak. This is a quartet, and we know that a quartet means that we have 3 neighbors of a different type. Now note, we have a triplet and a quartet. Most likely, these 2 functional or structural features will be connected together, because here we have a CH3, here we have most likely a CH2 because of the integration value of 2. And so since this has a CH3 and this has a CH2, this is a quartet and this is a corresponding triplet, most likely these 2 are connected. So most likely the CH2 and CH3 are connected to one another. Now moving forward, we have a singlet, which means that there are no neighbors. And most likely this singlet corresponds to a CH2. Right, again, we're looking at the most simple possibility that we can possibly have at this juncture. If we can't come up with a reasonable structure, then we can try to break this down into something more complex. Now note what happens when we get to this. And before we get to this, these 2 peaks here, let's go back really quickly to this one. Now some of you might think that there are 2 alcohols present, and we have 2 oxygens, so that could be reasonable. But before we jump down and try to assume that there are 2 alcohols present, let's move forward with our analysis using the most simple structural features that we possibly can have. So when we get to these 2 peaks, remember this is going to be an aromatic region peak. So this is the aromatic region. And note we have 2 nice doublets in the aromatic region. So there aren't going to be, in this instance, a bunch of overlapping peaks like we saw in the previous problem. But what we do know is that there are a total of 4 aromatic protons. So because there are 4 aromatic protons, we should know that most likely this benzene is disubstituted. Remember, a non-substituted benzene ring will have 6 protons on it, but we have 4 aromatic protons. So we need to get rid of 2 of those 6 by substituting our ring twice. Now take a look at the possibilities here. We could have disubstitution that looks like this, where X and Y are 2 different structures. We could have disubstitution that looks like this, where X and Y are 2 different structures. Or we could have disubstitution that looks like this, where X and Y are 2 different structures. Now what we need to try to figure out is which one of these 3 disubstitutions are most reasonable. And we're going to base this on the fact that our benzene ring has 2 equivalent doublets that are present. Again, we're basing this on the fact that our ring has 2 nice doublets, and we need to try to figure out which one of these 3 has the ability to give us 2 doublets. So take a moment and see if you can figure this out on your own. Hopefully, you guys have recognized that this is the only one that will give rise to 2 different doublets. And so now we can move forward. Now, this last peak that is in our structure, note that it is at 10 point, actually this is around 11. And so this is going to correspond to a carboxylic acid. And so now we know that these hydrogens from this peak do not equate to 2 alcohols because this is a carboxylic acid and both of our oxygens are consumed. We also see this is very broad as opposed to the sharp peaks that we are used to seeing. And so that further helps us to characterize this peak as being a carboxylic acid. So right now we have a CH3, a CH2, another CH2, we have a benzene ring with 6 carbons, and we have a carboxylic acid. If we count up all of the carbons that are utilized in these structural features that we have deemed associated with each of the peaks, we will have consumed all of the possible carbons that we have in our molecular formula. We will have also exhausted our hydrogens as well as our oxygens. So now the job for you is to put the structure together. Again, the goal here is to use all of the fragments that we have shown in this spectrum and piece this structure together the best way possible. So take a moment and see if you can piece this structure together. Push pause on your video, and then once you've found a reasonable structure and you've checked it with the splitting pattern, you're confident that you have got the right structure, then you can push play. But obviously, pushing play before is going to cheat you out of your ability to adequately solve these problems on your own. So once you guys have had a chance to go through this, hopefully everybody has gotten this as your structure. And you can see that this corresponds to all of the peaks that we see in the proton NMR. Now I will put the key up, actually before I leave tonight, I'm going to post this video as well as put the key up to the other problems, but be very careful about looking at the key. Again, looking at the key will automatically allow you to see exactly why your structure is wrong. So avoid looking at the key until you've double checked yourself, right? Double check your structure and its splitting with the spectrum, and make sure that you're very confident your structure is right before you look at the key.